The idea of Mars has always been seductive because distance feels abstract when seen through ambition. In images and animations, Mars appears close, familiar, almost reachable, yet in physical reality it is one of the most unforgiving destinations humanity has ever considered. At its nearest, it is tens of millions of kilometers away, and at its farthest several hundred million, which means that once a mission commits, there is no practical escape, no quick correction, and no external rescue. Unlike the Moon, Mars does not allow abort options because orbital mechanics, planetary alignment, and fuel constraints close every door behind the crew the moment they leave Earth. Long before Mars became a political goal or a media spectacle, one physicist warned that the hardest part of space travel was not departure but return. Richard Feynman did not frame this as philosophy or fear, but as an engineering fact grounded in physics systems, aging, and human fallibility. His warning was simple: technology fails quietly, not dramatically, and complex systems break through accumulation, not catastrophe. This principle becomes lethal on Mars because small degradations that would be manageable on Earth become irreversible verdicts millions of kilometers away. A Mars mission demands acceptance of a brutal constraint. Everything required for survival and return must either be brought from Earth or function flawlessly after years of exposure to radiation, dust, thermal cycling, and isolation. Anything forgotten cannot be replaced. Anything damaged may never be repaired. Oxygen, water, food, medical supplies, spare parts, energy, and psychological resilience are all finite and must endure a multi-year timeline without replenishment. Most critically, the return system must remain viable not for weeks but for years, while sitting idle in one of the harshest environments known. Mars return plans rely heavily on assumptions that systems will behave exactly as predicted. Engines will ignite after years of dormancy, fuel production will operate continuously, power will remain stable, seals will not degrade, software will not fail, and humans will perform optimally under extreme stress. Feynman repeatedly warned that engineering built on assumptions rather than demonstrated reliability is not conservative. It is fragile. On Mars, redundancy is limited by mass and energy, and failures are rarely independent because dust, radiation, and time affect every system simultaneously, maybe yet Ruben. Why he makes far less production, the cert argue, spinks it secretly exasperate. So always never receive it to I have. Mars return plans rely heavily on assumptions that systems will behave exactly as predicted. Engines will ignite. After years of dormancy, fuel production will operate continuously. Power will remain stable. Seals will not degrade. Software will not fail. And humans will perform optimally under extreme stress. Feynman repeatedly warned that engineering built on assumptions rather than demonstrated reliability is not conservative, it is fragile. On Mars, redundancy is limited by mass and energy, and failures are rarely independent because dust, radiation, and time affect every system simultaneously. The rocket equation dominates every attempt to leave Mars. Fuel is required to lift mass, but fuel itself adds mass, which requires more fuel, creating an exponential burden that quickly exceeds realistic limits. This is why modern concepts depend on manufacturing fuel on Mars using local resources, a process that must operate autonomously for months without contamination, mechanical failure, or power loss before humans even arrive. If fuel production fails completely, the mission is aborted. If it partially fails, the crew may land with no means of return. There is no margin for improvisation because ascent from Mars allows only one attempt and no rescue. Time itself is the most undefeated threat. A Mars mission spans years, not months, during which radiation alters human biology, electronics degrade, lubricants break down, plastics become brittle, and software errors accumulate. The spacecraft that attempts to leave Mars is no longer the spacecraft that departed Earth, and yet it is expected to perform with absolute precision. Mars actively accelerates this degradation through global dust storms, electrostatic particles, and extreme temperature swings that infiltrate joints, clog mechanisms, and erode power systems. On Earth, maintenance restores functionality. On Mars, maintenance consumes oxygen energy time and increases risk. Even if machines endure, humans may not. Years of isolation, confinement, delayed communication, and the knowledge that there is no rescue fundamentally alter cognition, decision-making, and stress tolerance. The return launch from Mars is not just a technical event. It is a psychological one, where hesitation, doubt, or minor error can permanently end the mission. Feynman understood that human error is not moral failure, but physical consequence, and that increasing pressure inevitably increases the probability of mistake. Feynman never claimed that going to Mars was impossible, but he warned against treating complexity lightly. Returning from Mars requires near-perfect planning, near-perfect machines, precise timing, uninterrupted support from Earth, and sustained human performance across years of degradation. Physics permits this outcome, but physics does not guarantee it, and reality does not forgive optimism, disguised as engineering. The fragility of grand plans. Every Mars return architecture looks coherent on paper, because paper does not age, suffer dust, or experience failure accumulation. Mission plans compress uncertainty into charts, schedules, and probability margins that appear manageable, but only because unknowns are averaged and long-tail risks are softened into acceptable percentages. This is not deception, but structural pressure, because no large space program survives without projecting confidence long before confidence is justified. As a result, Mars return plans are optimized for approval rather than resilience. One of the most repeated assurances is redundancy, the idea that if one system fails, another will replace it. This principle works in environments where mass power and maintenance are abundant, but on Mars, redundancy is limited by physics. Every additional system increases mass power, consumption, complexity, and failure modes. More critically, failures on Mars are not independent because radiation, dust, thermal cycling, and time degrade all systems together. When systems age in the same environment, they fail in correlated ways, making redundancy far less protective than assumed. Testing cannot close this gap because Mars return systems cannot be fully validated before use. Multi-year exposure to deep space radiation cannot be reproduced precisely on Earth, nor can Mars dust thermal cycles or long-duration isolation be simulated at full scale. Engineers test components in fragments, valves in vacuum chambers, electronics under radiation, software in simulated timelines, habitats in analog environments, but the complete integrated system exists only once, millions of kilometers away with human lives attached. This substitution of experience with confidence was something Richard Feynman repeatedly warned against, because partial testing cannot guarantee whole system behavior. Political and institutional timelines further distort risk assessment. Physics does not care about budgets, elections, leadership, turnover, or public enthusiasm, but missions must align with all of them. This pressure reframes unresolved problems as future work and unknowns as engineering challenges, rather than blockers. Safety margins are eroded not by ignorance but by optimism, because waiting for certainty means never launching, while launching early accepts irreversible consequences. Mars does not allow iterative learning because failure cannot be analyzed and corrected after the fact. Energy availability becomes a continuous constraint rather than a background assumption. Solar power on Mars is weak, unreliable, and vulnerable to dust, while nuclear systems add mass heat and political complexity. As energy margins tighten, crews are forced to prioritize survival over diagnostics, maintenance over investigation, and operation over repair. Degradation accelerates quietly as reasonable decisions accumulate into irreversible states. Mars return failures would not appear as explosions, but as calm realizations that systems can no longer be trusted to perform ascent safely. Software introduces another invisible vulnerability because modern missions are computationally dependent. Navigation, life support, fuel synthesis, thermal control, and engine ignition are governed by millions of lines of code that cannot be exhaustively tested against every possible state combination. Software does not wear out, but it reveals latent assumptions through rare interactions, timing drift, and unexpected sensor behavior. On Earth, updates, patches, and reboots mitigate these issues. On Mars, communication delays and system interdependence turn minor bugs into mission-ending conditions. The concept of Mars-proven technology further masks fragility. Hardware that survives unmanned operation for limited durations is not equivalent to systems required to perform high-stress operations after years of dormancy. Survival as passive ascent is violent, and engines that have aged in radiation, cold, and dust must ignite flawlessly on the first attempt. There is no precedent for this requirement, and no fallback if ignition parameters deviate even slightly from nominal behavior. Human performance is often treated as constant, despite prolonged exposure to reduced gravity radiation, isolation, and stress. Over time, bone density, muscle strength, cardiovascular response, and cognitive sharpness change in ways that are difficult to predict. Emergency procedures assume rapid movement, clear judgment, and physical resilience precisely when those traits are most compromised. Treating humans as stable inputs rather than adaptive systems introduces another layer of unmodeled risk. Finally, Mars enforces silence. Communication delays eliminate real-time assistance and force crews to diagnose and act without confirmation or correction. Missed interpretations, hesitation, or delayed decisions can cause launch windows to close permanently because orbital mechanics do not wait. When that window closes, the mission does not pause, it ends. Mars return plans appear safer than they are because probabilities of averaged failures are assumed independent and rare events are discounted. But Mars allows no retries and no learning from mistakes. With only one attempt, probability loses meaning because the outcome is not a statistic, it is a verdict. The point of no return. Every Mars return plan quietly avoids the most important question: what happens if the crew cannot come back? Because this question has no technical solution, only consequences. Mars is too far for rescue missions, launch windows are too rare, and resources are too constrained to allow recovery. Once ascent fails, a stranded crew is not a temporary crisis, but a terminal condition, because there is no realistic pathway for intervention, correction, or evacuation after failure. Mars return is defined by a single irreversible moment, the ascent. There is one vehicle, one fuel supply, one ignition sequence, and one narrow launch window determined by orbital mechanics. If the engines fail to ignite, if thrust is insufficient, or if guidance deviates beyond tolerance, the mission ends permanently. Unlike Earth-based systems, there is no opportunity to analyze failure, learn from it, and try again. Reliability normally emerges from repetition, but Mars allows only one attempt, which eliminates statistical confidence entirely. This reality introduces an ethical dimension often disguised by language. Publicly, Mars missions are framed as round trips, but privately, many planners acknowledge that early missions may effectively be one way, even if return hardware is present. Consent and courage do not transform fragile systems into reliable ones, and willingness to accept risk does not substitute for demonstrated capability. Framing abandonment as heroism does not change the underlying fact that survival depends on uninterrupted perfection across years of degradation. When return becomes uncertain, the narrative often shifts from mission to settlement. Colonization reframes failure by redefining it, but this is a psychological maneuver, thus not a logistical solution. A stranded crew does not become a self-sustaining civilization by renaming their condition. Mars cannot support industrial independence, medical self-sufficiency, or long-term biological continuity without constant Earth support, and that dependency introduces another failure mode entirely. Every Mars survival scenario assumes Earth remains stable, technologically capable, and politically willing to support Mars indefinitely. Any disruption on Earth, war, economic collapse, leadership change, or loss of public interest can sever that support. Mars crews would exist at the end of a supply chain dependent on decisions made on a planet they can no longer reach. Complex systems fail not only internally, but when their external environment changes, and Mars magnifies this vulnerability. The psychological weight of knowing there is no rescue fundamentally alters human behavior. Risk becomes inevitability, and decision-making shifts under that awareness. Caution can turn into paralysis, confidence into denial, and delay into permanent loss of opportunity. The final launch from Mars would not feel like triumph, but judgment, because pressing the ignition sequence is an irreversible commitment with no fallback. Public narratives emphasize flags, milestones, and legacy, while physics focuses on mass energy degradation and failure rates. This mismatch creates false confidence because success is communicated as inevitable rather than conditional. Richard Feynman warned that when public relations outruns reality, disaster follows not because of intent, but because nature eventually asserts itself. Mars return is a promise physics has not agreed to honor. This argument is not opposition to exploration, but insistence on sequence. Human progress has historically advanced through incremental exposure, with escape routes, resupply, and learning from mistakes. Mars return bypasses this progression by demanding sustained perfection before sufficient experience exists. Admitting this limitation is not weakness, it is engineering honesty. Returning from Mars is not forbidden by physical law, but it requires conditions human systems have never maintained: flawless multi-year operation, zero critical failure, uninterrupted institutional support, and consistent human performance under extreme isolation. Calling this inevitable replaces analysis with aspiration. The danger is not attempting Mars, but convincing ourselves that success is guaranteed and designing missions accordingly. Physics permits return, but reality does not grant forgiveness, and Mars will not negotiate with optimism.